Hi everyone. I'm Nicholas Coltharp. Um, I'm sorry. I'm Nicholas Coltharp. I'm a PhD student at Portland State University. This is work that was done in collaboration with Stephen Libby at Oregon State and Laura Israel, who's currently at the University of Constance, and Yao Li, my advisor. And the title of this paper is Unifying Hindsight and Foresight, Lazy Cost Analysis as Functional Logic Programming. So this is a talk about the time analysis of programs written in a lazy programming language, okay? So I'd like to start by reviewing why this problem is hard. So we have here a typical definition of the append function in a lazy language or in a functional language. I think most people have probably seen this before. So you're appending two lists together, right? You case on the first list. If it's empty, you just return the second list. And if it's something followed by something else, then you just put that first element on, and then you make a recursive call. And we're asking the question, given X's and Y's, two lists, what is like the total cost to evaluate this all the way down to a value? So in a strict language, you'd say, well, it's O of M, where M is the length of X's. In a lazy language, maybe you say, oh, well, if we're evaluating it all the way down, well, X's and Y's, they could be funcs, right? So, we have to take into account the cost to evaluate those two things as well. So it's like, the OM plus the cost to evaluate X's plus the cost to evaluate Y's. But what if I do this? If I have, instead I say that X is equal to something, some expensive computation, and Y's is equal to X's. Well, then when I go to append them, I'll have to evaluate X's once. But then when I go to evaluate Y's, well, it's essentially the same as X's, right? So I don't actually have to do anything to evaluate it all the way down to a value. So the point I'm trying to get across here is that the cost, the time and performance of a lazy program is non-compositional, right? I can't just look at an expression in isolation. Variables don't cost a constant amount to evaluate, unlike in, say, call by value or even call by name, where in call by name a variable costs a certain constant. So this is the basic problem. So what's the cause of this problem? Well, one answer we could give is that the cause is the semantics we're using. The typical semantics of lazy languages is you carry around this heap that maps variables to generally expressions. And when you go to look up a variable or evaluate it, you check whether it has been evaluated already. And if it hasn't, you evaluate the expression it's bound to, and you replace it in the heap. And then further attempts to evaluate that variable, they don't cost anything, essentially, because they are already evaluated. So if the problem is the semantics, maybe we should change our semantics. So in recent years, a couple of semantics have been proposed to help alleviate this problem. I'm going to sort of run by these really quickly, and then I'll come back around later and sort of go into it in more detail. So the first one is clairvoyant call by value, or just clairvoyant semantics for short. The way this one works is when you go to evaluate a computation that in the standard semantics would be thunk, so a lazy computation, you don't defer evaluating it. Instead, you either immediately evaluate it, just like you would in call by value, or you simply discard it, you throw it away. It turns out that this way of evaluating things can give you performance or semantics that is equivalent in a certain sense to the standard lazy semantics. So I'm going to make I think the pretty bold claim that this is a fairly simple and straightforward semantics. It may not seem like that right now, but I'm going to try to come back and justify that later. But the problem is that it is effectively non-executable. Because, like I said, you either immediately evaluate a computation or you discard it. That's non-determinism. And so we don't really want to be directly running this. The other alternative that I'm going to talk about today is called demand semantics. The way this works is a computation, a lazy computation occurs in a context. And that context tells you how much of the computation's result is eventually going to be needed, right? So if I'm appending two lists together, I'm showing here X's and Y's, and I'm saying X's is in some sense related to the singleton list 1, and Y's is related to the singleton list 2. If I add them together, how much it costs to evaluate that depends on how much of the result I'm eventually going to need, right? I could take a length 1 prefix, and then it's only going to cost a certain amount. I could take a length 2 prefix, is going to cost a certain amount, a different amount. And so the idea here is that you have this sort of two-way evaluation where at the same time you're evaluating both forwards and also you're carrying information backwards about what parts of the result you're going to need. And this is a different way to evaluate costs. The nice thing about this one is that it's executable. So I can actually plug in a demand and get back an actual result, including an actual cost. But it's complicated. It's difficult to explain. It's difficult to write down. Yeah, so these are the two alternatives, the two alternative semantics I'm going to talk about. They have sort of contrasting benefits and drawbacks. And so the question is there a way that we can do better? I'm going to say the answer is yes, by unifying the two semantics. So finding a way to express both of them simultaneously. How can we do that? We're going to use logic programming. So this is the story about how we use logic programming to solve this problem. Specifically, here are our specific contributions. We have a method for translating functional code to logic programming code that simultaneously expresses the two semantics that I've just outlined. This is a practical method. We have several case studies implemented in Curry that use this method. And we have a formal definition of the translation, along with a mechanized proof that it actually does what we say it does. And we have benchmarks of the resulting code also, which demonstrate that it is acceptable for some purposes, which I'll get to in a bit. Okay, so let's go back to clairvoyant semantics. This is, I claimed, the simpler of the two semantics. So this is called clairvoyant call by value sometimes, or it was originally called clairvoyant call by value. And the reason why it's called that is that it is indeed analogous to call by value. So here, I'm appending two lists together, the singleton lists 1 and 2. And the universe is going to split when I try to do that. In one case, I'm going to evaluate the recursive call, which I've represented here. In the other case, I'm going to simply throw it away. This bottom term here, this bottom value here, represents a computation that's been thrown away. I'm just simply going to ignore it. I'm not going to use it. Now, the question is, right? Oh, and of course, it goes all the way down. And if you follow the arrows, that'll tell you in this case how much it's going to cost to evaluate this expression. So we're going to say for our purposes that a function call it incurs a unit of cost. And this is called clairvoyant call by value because of the following question: what happens if you're in this universe where your result is 1 cons bottom? So I just threw away the rest of the result. What happens if you're in that universe, but you ask for the first 2 elements of the resulting list? The answer is that the computation just gets cut off. So if you're in that universe, you fail. You simply can't be in that universe. And so it's clairvoyant because you're essentially saying, well, ahead of time, I have to know which set of which computation path is the correct one to take in this sort of like forest of splitting possibilities. And of course, you could always evaluate more expressions than you need to, but it turns out that if you take the minimal cost result, right, the branch that terminates successfully and gives you the minimal cost, that's equivalent to the cost you would get in the standard semantics for lazy evaluation. Oh, yes?
maybe I missed something, but I failed to realize why for lazy evaluation.
Yeah. Oh, yes. So, I mean, the point is, right, in lazy evaluation, when I go to evaluate an expression, I don't evaluate it right away. I store it, and then later, if I need it, I evaluate it, right? This just says, actually, I'm not going to wait. I'm just going to either evaluate it right now, or I'm never going to evaluate it, right? And the tricky thing is, right, it turns out that making the locally optimal choice always gives you the globally like correct result. Does that make sense? So it's like, it doesn't matter when you evaluate an expression, just whether you evaluate it.
Okay, so this means that in the case that I took the first, the one with the bottom, it just means that, oh, in my execution, I was just looking for the first element. I didn't care about the rest.
If you ended up in the first one, yes, that's right. Then that's where you only took a length one prefix of the resulting list. You didn't ask for anything else. That's right. Yeah. Okay. So I'm going to present a framework for modeling clairvoyant semantics in the programming language Curry. For those of you who are not super familiar with Curry, it's just like Haskell, but it has logic programming features bolted on. So that includes free variables and non-determinism. So we need to keep track of costs. So we have here what I'm calling the tick value. If for people who are familiar with monads, this is indeed just a writer monad over the additive monoid of natural numbers. But the basic point is that value of tick represents a computation or a result with some cost attached to it, telling me how much it took to compute that thing. We can sequence tick values, so we can do one and then do the other, and then we just add the cost together. And we have a primitive operation which just incurs a unit cost. And this is, we're just, whenever we need to say, oh, we're incurring a cost, we'll just insert that, at the point where we need it. Okay, here comes the more complicated stuff. So we need some way to represent computations that we may or may not evaluate. That's this t value here. It's either undefined or a thunk. Undefined means we're going to skip it. Thunk means we didn't skip it. We also need a way to either run or not run computations with costs, and that's what this thunk combinator does. So the question mark here is Curry's non-deterministic choice operator. It means either do the left-hand side thing or the right-hand side thing non-deterministically. So we either simply skip, that's undefined, or we just run the computation that we're taking as an argument here. There's a couple other combinators. Force projects out from a computation that may have been skipped to get a value. And you can see that force undefined is an error. It's not defined. And in Curry, that just translates to that computation branch gets cut off. So if we end up needing a result, then or the result that we skipped, and that computation branch will just get cut off. Forcing is similar, except we are running an action on the result that gets forced. With combinator is a little more complicated. It just says we have a value that may have been skipped. We're going to extract it and do something with it, or we're just going to skip. There'll be an example coming up. Hopefully that'll clear it up a little bit. Okay, so we're working with our running example of list append. So we need a way to talk about lists that are spine lazy. That's what this list type is. And we're choosing to represent lists as being spine lazy, not necessarily head lazy, or like not necessarily lazy in the values they contain. So the important thing here is you have this cons constructor, and the tail is wrapped inside a tick, so it may be skipped. And this corresponds to the usual way that lists are used in Haskell, where they are used in a spine lazy way, or in like a streaming way. So here's the append function. Every call incurs a unit cost, right? We have a tick at the front. This F case is Curry's flexible case. used because case and curry residuates. So if you apply it to a logic variable, essentially, it will probably halt in most curry compilers. Fcase uses Curry's narrowing strategy, which is its usual evaluation strategy. So we case on the first list, and then when we come to the case where the list is a cons, the tail is spine lazy, right? So the tail is wrapped in a thunk. So we need to extract it and then do something with it. So that's why this append recursive call is inside the with combinator. And then finally at the end, we just return a cons like usual. So that's clairvoyant semantics, and that's an implementation of clairvoyant semantics in Curry. So now demand semantics in detail. So the idea here, I'm representing the demand on a value by an equation. So I'm saying append x is y is equals 1 cons 2 cons bottom. With the constraint x is less than or equal to 1, y is less than or equal to the singleton list 2. What I'm really saying here is I want the result. I'm using the result of this call, append singleton list 1, singleton list 2, in a context where I'm going to ask for the first two elements, but nothing else. So here, before bottom represented a skipped computation. Now it represents a computation that I'm not going to ask for. Okay, it's a computation that I'm not going to demand at the end. Formally, the way this works is I'm going to feed in some value that's an approximation of the actual result. That's what this is here. So by actual result, I mean, if you appended these two, you would get the list 1, 2. This is a demand on that result, telling me how much of that I'm going to want. And then I get out a set of demands on the variables in scope. Okay, so it essentially goes backwards from how much of the result do you want to how much of the ambient environment are you going to need, plus the cost to evaluate that. So how does this work? Well, we're going to start by evaluating this append call one step. Now, how could you do that? I've said x's and y's are variables here. We're going to do that by just assuming that x's and y's are in fact these values that I've said they're related to. So I'm going to say, pretend x's is just a singleton list 1, y's is just a singleton list 2, reduce this append call once. And I get one cons onto a recursive call where x's prime is some Dunning variable that I've introduced. The important thing is that x's prime has to be less than the empty list, essentially by the fact that by construction. Essentially, the point is that the only way I can get this here with these constraints is if this new dummy variable here is related to the empty list. That already tells us something, which is that x's has to be 1, right? Because it has to be related to the singleton list 1, but its tail has to be empty. So it has to just be the singleton list 1. And that's feeding information backwards. If we go one more step, we get information about y's. We find that y's has to be 2 cons onto don't care, right? So we're finding that at the end, we need to know everything about x's because we're asking for a length 2 prefix, right? So we have to consume x's all the way. We don't have to know everything about y's. We just have to know what its first element is. Because again, we're only asking for the first 2 elements of the resulting list. And if you look at the number of links between these, this will tell you that the cost to evaluate this is 2. Right? So the number of steps here is 2, the cost is 2. Okay.
Could I ask you something?
Oh, yes.
You go to the slide.
Mhm.
How do I get the first stage?
Sorry?
How do I get the first stage of this computation? So this means that I'm in the state where I want I know XS is the singlet in this, YS is the singlet in this,
Mhm.
and I want to know the value of a to append XS YS. So how do I get to the first state of this conversation?
So just this right here.
Yeah, exactly. And the constraint source.
Yeah, so I'm presenting it in a slightly modified form from the usual presentation. But the idea here is that I'm trying to look at actually the call is append how can I put this? So I know that what I'm saying here is that I know that X's is an approximation or a demand on some list one, some singleton list one. And I know that Y's is an approximation on some singleton list two. And the way I mean, you could imagine this by like, you enter into the Haskell REPL, append singleton list one, singleton list two, right? In that case, you know that the result is going to be some approximation of 1, 2, depending on how much you ask for, depending on the context in which it occurs, right? So that's how you end up in this situation, right? And this equation represents the context, right? Or how much I'm going to end up using. So if you have this equation that represents take two of the result, does that make sense?
Yeah. Okay. Thank you.
Okay, those are the two semantics. We want to find a way to sort of express them simultaneously. So I struggled with how to represent this, the intuition for why this works. But this is what I came up with. So we have here this tree of computations that I showed before. Here I'm also presenting a demand, like I did in the demand slide. So we have it that X is an approximation of the singleton list one, Y is an approximation of the singleton list two, and we're demanding the first two elements and nothing else as before. Okay, well that actually cuts off this first branch here, right? Because we're demanding more than the amount of information contained in this branch here. So we simply cannot be, if we're thinking of clairvoyant semantics as non-deterministic, we simply cannot be in the universe where we don't compute the second element, right? Because we're demanding more than that. Okay, so we have to go here. So we can infer information about X's from that just as before. This is all the same information we inferred in the demand semantics slide. And if we keep going, right, well, this works, right? If we just try this branch here, right, this gives us the demand that we asked for to begin with. And that gives us information about what Y's is. So this is the intuition for our technique. So this is the way it actually looks when it's implemented. So we have this append D function, which is the counterpoint to the append C function I showed before. Here, I've highlighted everything that represents either the first list input argument or a demand on it. Okay, so we're taking in two list T arguments or list A arguments. Those two arguments are the values the list we're appending together, plus a final list argument that represents the demand on the result of appending these two lists. So it's how much we're going to need. And then we return, in addition to a cost, how much of those two inputs we're going to need. Right, so this first element here corresponds to a demand on this first argument here. This second element here corresponds to a demand on this argument here. And all we have to do is we have to postulate a free variable. Free variable in Curry speak is essentially a logic variable. Postulate a free variable for the demand on this result. Constrain it to be related to the actual result. Similarly for the second argument. And we just have to say that when we run this through clairvoyant semantics, we get the implied demand or the supplied demand along with some cost. And then we just return that cost. And I want to postulate or put forth like the following basic slogan. Clairvoyant semantics corresponds to non-deterministic choice, maybe not that surprising considering that it is essentially just non-determinism. Demand semantics corresponds to constraint solving. The key here is these constraints on that impose a relationship between the demands and the values that they're demanding, and also on the result of the append call. I will probably rush through this a little bit because I'm a little short on time. The point is that we need a way to talk about whether a value approximates a certain value. This is more or less what you'd expect. The only thing to note here is that undefined is always less than anything. Otherwise, like if you have an empty list, it's less than the empty list, and if you have two conses, then it works algebraically. So a cons is less than a cons if the head is less than the head and the tail is less than the tail. It works like that otherwise for every data type you could ask for. But I want to bring this in. This previous method has some performance problems. It doesn't work. It doesn't perform very well because I'm postulating a bunch of free variables, and those free variables could be anything. And it turns out that Curry will just try everything. So instead, we're going to say, well, actually, given a value, we're going to have a method of prox that simply generates all possible values that are less defined than that value. And that restricts the search space and makes it more efficient. I mean, I have a default implementation here that just does the bad thing, but you can provide a better implementation for specific data types. For example, here, undefined, if we're talking about an instance for T, undefined is less than everything, but also if I have a thunk, I can also thunk of a prox of the value. And because Curry has non-deterministic or nonlinear, Curry has nonlinear non-deterministic patterns, right? So both of these patterns will match for a thunk value, and it will non-deterministically. And here, this is the what we get out if we use that approx function instead of just free variables like we used before. Okay, so should you trust us? Should you trust that this method works? The answer is yes. We have mechanized proofs in Agda. Essentially, we showed that if you we gave a formal definition of these translations from a functional language to a logic language. The clairvoyance translation, the insert C the append C that I showed before, performs exactly like the clairvoyant semantics of the original term. The story for demand semantics is a little more complicated. It turns out that as for the theorems as proven do not give you exactly the same result as demand semantics. I have an argument, I think, for why it should actually be the exact same result, but I haven't run that by anyone yet, so I don't want to like make that claim too strongly. We have several case studies implemented. I won't go into these in too detail here. I do want to mention that the demand translation as presented is not completely deterministic. You need some kind of support to select one element, but it turns out that if you just always for example in Curry provides a function to always select one element of or always to guide the search space, and it turns out that if you always say take the left branch, whatever the less defined branch of the computation is, you'll always get the right result. So you can make a locally correct choice that always ends up giving you the correct result. Yes. This is the essence of clairvoyant semantics, right? That if you make the locally correct choice, you'll always end up with the globally correct choice. So the method the performance of this method is in some ways somewhat questionable. This is an example of an insertion sort demand function. And you can see that the performance for 100 elements is 6 seconds, which is not so great. But for our purposes, it might be enough. We're using it to test implementations against handwritten implementations in Rock, or that's the way we've used it so far. For that purposes, a small number of elements is okay. It turns out, usually if your implementation is correct for a fairly small number of elements, then it's probably correct for like 100 elements. Okay, that's my talk. Thank you, and I'll take any questions.